You've probably been there. You spend weeks building a machine learning model. The tests look great, but the moment it sees real-world data, it just doesn't work. It's one of the most common frustrations in this field.
So why does that happen? Why is there such a huge gap between how a model performs in training versus how it performs in reality? This is a really fundamental question.
It often looks something like this: 99% accuracy on your training set, but then it drops to 60% out in the wild. By the end of this, you'll understand the two core reasons this happens. They're called bias and variance.
To really get this, we're going to put aside the math for a moment. First, let's just build a solid, intuitive feel for what's going on. Okay, so imagine we have some data points, and let's say there's a true underlying pattern to them, a nice smooth curve. But the points themselves aren't perfectly on that curve. They're scattered around it because of random noise. Our job is to find the real pattern, the signal, and not get distracted by that noise.
So for our first attempt, let's try to fit a really simple model to this data: a straight line. Right away, you can see the problem. A straight line just can't capture that curved shape.
This model has what we call high bias. It's making a strong but incorrect assumption that the relationship is linear. It's just too simple, and it completely misses the real pattern. We call this underfitting. You can think of this model as being too stubborn.
All right, the simple model didn't work. So let's swing to the complete opposite extreme. This time, we'll use an incredibly complex model, one that's so flexible it can perfectly weave through every single data point.
Now, this looks perfect on our training data, right? But it's actually learned the wrong thing. It hasn't learned the underlying signal, it has memorized the random noise. This extreme sensitivity to the training data is called high variance. If we gave it a new batch of data, its predictions would be all over the place. This is overfitting. You can think of this model as being too impressionable.
So neither extreme is what we want. The ideal model is somewhere in the middle. It's flexible enough to capture that true curved pattern, but it's not so flexible that it starts chasing after every little bit of noise. Finding this balance is the real goal.
Now, let's connect this intuition to some formal definitions. Bias is the error that comes from a model's overly simple assumptions. It's like the model's built-in prejudice. A high bias model will consistently miss the mark, even if you give it more and more data.
And variance is the error that comes from the model being too sensitive to the specific data it was trained on. A high variance model is unstable. If you trained it on slightly different data, you'd get a completely different model.
This leads to a really important insight in machine learning. A model's total error isn't just one single number. You can actually decompose it into a few distinct parts.
The total error is the sum of three things: the bias squared, the variance, and something we call irreducible error. That last one is just the inherent random noise in the dataset itself. We can never get rid of it. So our job is to focus on minimizing the other two.
And this is where the trade-off happens. As you make a model more complex, its bias tends to drop, which is good, but its variance tends to rise, which is bad. The sweet spot, our best model, is right there in the middle, where that combined error is at its lowest point. This is the bias-variance trade-off.
Okay, this makes sense in theory, but how do we actually use this idea to build better models in the real world?
Well, for starters, different algorithms have different personalities. Simple models, like linear regression, tend to be high bias but low variance. On the other end, a single deep decision tree tends to be low bias but very high variance. And then you have methods like random forests, which try to get the best of both worlds by averaging a bunch of high variance trees to lower the overall variance.
We also have specific techniques to manage this. Regularization, for instance, adds a penalty for complexity, which directly helps to reduce variance. Bagging, like we just saw with random forests, is also great for reducing variance. Boosting, on the other hand, is a technique that's really good at reducing bias, and cross-validation is our main tool for finding the right settings that balance the two for our specific problem. So the most important thing to remember is that you can't eliminate both. The goal is not to get bias to zero or variance to zero. The goal is to find the right balance between them that gives you the lowest possible error on data the model has never seen before.
Ultimately, a model is only valuable if it can generalize. Its ability to accurately see patterns and then apply that knowledge to new situations is what matters. And managing this trade-off is how we get there.
So the next time a model isn't working, ask yourself this question: is it being too stubborn or is it being too impressionable? Answering that will point you in the right direction.